In the spring of 2021, with a return to the daily commute looming, I added a midday bike ride to my routine to get as fit as possible before losing my freedom. I didn't bother with sunscreen, reasoning I could stay in the shade almost the whole way. It took only a few days to realize how wrong I was, but the reason is one that's worth knowing. In today's video, why the sky is blue, why it took so long for us to figure that out, and what it all has to do with how we see the world and the importance of science in our everyday lives. Why is the sky blue? Why is space black? What does it mean to see anything? And what's that got to do with sunburn and science? It seems simple enough. Just open your eyes and look around if there's enough light. Sunlight, moonlight, torchlight, it doesn't matter. Though there are all kinds of light, and light can warm you as well as showing the way. But wait, how is that exactly? If temperature is a measure of the jiggling of molecules in a substance, what's that got to do with light? And why does light do so many weird things like bending as it travels through water, refracting through a lens, even forming interference patterns? Light isn't so simple after all, and in fact, it's only in the last couple of centuries we've even started to understand it. How light works, in fact, is the subject of much of the revolution in physics that surrounded the start of the 20th century, and it's far more than we need or can cover in this one video. Instead, let's start with some easy things. The ancients had some very odd ideas about light. Some even thought the eyes somehow reached out magically to probe the environment around us. In reality, of course, it's the other way around. We see by sensing photons of light that reach our eyes after being reflected off of or being emitted by objects around us. A red dress is red because it reflects red light. That is, light of a certain frequency range we perceive as red. A white sand beach, on the other hand, reflects every frequency that we can see, and we perceive that as white. Space reflects nothing, so we perceive it as black. Already, we can see that light is kind of weird. Depending on how we study it, it can have wave-like or particle-like properties. But it really isn't either. It just is what it is. The important thing here is that, like so many things, light can defy our everyday expectations. I often see people online asking why the Apollo astronauts went to the moon at night. The answer, of course, is they didn't. The lunar sky is always black, even at high noon. Space is a vacuum, a lack of anything. So there's nothing in space to stop light streaming out from the sun from just continuing on its way in whatever direction it's going. We can't see it as it streams past because there's nothing to bounce it back into our eyes. Except for the shadows of Earth and our moon, the space around us is filled to the brim with sunlight. It's all just out of our reach. On Earth, things are different. We see a bright daytime sky because air, moisture, pollution, and dust bounce sunlight all around us, and some of it reaches our eyes. That's simple enough, but then why is the sky blue particularly? A sunset red or yellow? Our eyesight and intuition can only take us so far, and it took a very long time in the rise of scientific inquiry to answer this simple question, and with some intriguing surprises along the way. In 1800, astronomer Wilhelm Herschel, while trying to make a filter through which he could safely observe the sun, used a prism to split sunlight into its various colors and a thermometer to measure the heat produced by each color striking a surface. As he expected, he found that different colors heated his thermometer by different amounts, but surprisingly, the most heating occurred on a thermometer placed beyond the red end of the visible spectrum, where there appeared to be no light at all. He concluded there must be some invisible color beyond red that's effective at carrying what we still call radiant heat. He was right, and this invisible light is now called infrared, meaning below red. We can't see infrared light, but we can feel it when we hold our hands to the sun or to a hot oven, and it warms our skin and nerves. It feels hot, and we talk as if it were a kind of heat, but it really isn't. It's light. Infrared light is electromagnetic radiation just like radio waves or X-rays or visible light, only of a frequency that's readily absorbed by the outermost electrons of most materials. When that happens, the energy of the light contributes kinetic energy to the molecules in that substance, making them jiggle around more vigorously. Infrared light isn't heat, but its absorption increases the molecular jiggling that is, whether we feel it on our skin or measure it with a thermometer. So Herschel discovered infrared light, and a year later, German physicist Johann Wilhelm Reiter reasoned that if invisible heat rays existed below the color red, invisible cooling rays might exist at the other end of the spectrum, above the color violet. What a cool idea! And it would have been cool, pun intended. But while he didn't exactly find cooling rays, his logic wasn't completely off. What he actually found were invisible rays that darkened paper soaked with silver chloride, a simple precursor to what would soon become photographic emulsion. He discovered another invisible type of light, what would come to be called ultraviolet, meaning beyond violet. And he'd confirmed the power of scientific inquiry to reveal the unseen world around us. Light below the UV range, all the way through visible light, down through the infrared, past microwaves, and all the way down through the radio range can heat things up, but it can't break chemical bonds. Your microwave oven cannot turn your burrito into frankenfood. They already did that at the factory. Light of higher energy, from the UV band up through X-rays and gamma rays and beyond, can break chemical bonds, and so it can injure living things. But these discoveries were all still far in the future. Surprises were still to come. In the 1860s, while attempting to purify air for his investigations into what we now call the greenhouse effect, Irish experimental physicist John Tyndall discovered that bright light scattering off extremely small particulates appeared faintly blue. This led him to speculate that this might be what gives the sky its characteristic blue color. In the following decades, English physicist Lord Rayleigh studied this effect, eventually showing that it follows from James Clerk Maxwell's 1865 proof of the electromagnetic nature of light, and applies not just to dust, but to molecules. To understand this, remember that visible light is just a tiny sliver of the broader electromagnetic spectrum that stretches from gamma rays all the way down to radio. Maxwell had shown that light can act like a wave or vibration of simultaneous electric and magnetic fields, thus interacting with both. The way this happens was fascinating but stunningly counterintuitive. Moving electric charge creates a moving magnetic field, which creates a moving electric charge, which creates a moving magnetic field, and so on and so on. This is a simplification, of course, but the result can best be understood as an electromagnetic wave that propagates itself at the speed of, well, you guessed it, light. Maxwell explained how light propagates as an electromagnetic wave through empty space. Rayleigh then showed that molecules and tiny particles, though neutrally charged overall, can have non-uniform distributions of positive and negative charge that form tiny electric dipoles in space, in much the same way that permanent magnets form magnetic dipoles. Just as a magnetic field deflects a compass needle, Rayleigh showed that the electric component of an oscillating light wave acts on the charges within particles, causing them to resonate very slightly at exactly its frequency. This oscillation of electric charge starts Maxwell's whole electromagnetic wave mechanism going, causing the particles to emit more light of their own, and at the same frequency as the light that set them wiggling. Essentially, tiny particles act like little antennas that collect some of the light hitting them and then radiate it away at exactly the same frequency, but in a random direction. They scatter the incoming light. Today, this is called Rayleigh scattering, and the degree to which it happens is inversely proportional to the fourth power of the wavelength of the light. Shorter wavelengths like violet and blue light scatter far more than longer wavelengths like yellow and red, and that's why the sky is blue. Red and yellow photons mostly pass straight through the atmosphere, much as they do through a vacuum. Blue light, however, scatters all over the place, and so reaches us from all over the sky. The color of the sky is the product of this scattering, the color distribution of light arriving from the sun, the absorption of certain wavelengths such as far UV light by the atmosphere, the composition of the atmosphere, the angle the light takes through the atmosphere, and a few other smaller factors. The daytime sky is blue because blue light is preferentially scattered by molecules of nitrogen, oxygen, and water vapor. The sun looks slightly yellow because some of its blue light has been scattered away by the atmosphere. Sunsets are often red because when the sun is near the horizon, its light is passing through so much air that most of the blue has been scattered away into someone else's sky. And finally, stormy skies are gray and clouds white because Rayleigh scattering is also a function of particle size, and the droplets and ice crystals that make up clouds scatter all frequencies of light equally. So what's this got to do with my skincare regime? Well, sun tanning, skin cancer, and premature aging of the skin are all caused mostly by UV light, because it's right at the point in the electromagnetic spectrum between visible light and X-rays where light just starts having enough energy that a single photon can break chemical bonds. Most of the more dangerous end of the UV spectrum is fortunately absorbed in the upper atmosphere, but the rest reaches us where it causes tans and ages our skin. And if blue light scatters off air molecules more than the rest of the visible colors, it stands to reason that UV light, which is higher on the spectrum, is scattered even more. This means you can't really hide from sunburn under a shade tree, because UV light shines down about equally from all over the sky. Deep shade will block red and infrared light, and that will help you shake the summer heat. But unless the shade is broad enough to completely blot out the sky, like say in a cave, it won't have much effect on blue or UV light, or on your risk of developing skin cancer. So, when you go out for your daily jog or bike ride, make it early or late when the sun is low enough on the horizon that most of the UV is absorbed before it can reach you, or slather on a good sunscreen. Riding in the shade won't save your hide, appearances notwithstanding. Appearances come through senses optimized for keeping our ancestors safe and fed in the wilds of Africa, without consideration for the principles and laws that underlie our world. Science is nothing but a systematic way of getting at those deeper truths by careful study of reality. When we speculate based on superficial observations and don't bother to test our ideas, we are almost certain to be wrong. If something as simple and commonplace as sunlight can hold such hidden mysteries, imagine what others lay hidden around us as we go about our lives. If you liked this video, please go ahead and hit the like button. And if you haven't already, subscribe and hit the notification bell so you won't miss any of the science goodness. And if you want more of my science and science fiction, you can support my writing on patreon.com or buy my sci-themed merchandise at teespring.com. You can also find me on Amazon and audible.com. It's kinetic energy to the molecules in that substance, making them jiggle around more bigger. I must have swallowed some infrared light. Davy? What is a Davy? Does anyone know what is a Davy? Say hello, Mr. Lucky. Say hello, little sleepy dog. Don't lick my nose, that's gross.